the 0 did not appear even with, okay, fine. Should be a 0 here. So you consider the subspace of all L infinity controls with 0 mean, right? And then you fix alpha greater than 0. And you choose V in this way. Essentially, L2 is free. You can do whatever you want with the L2 part because the problem is in the first control. And, well, essentially, you want to choose V1 infinity in such a way that every element here has the property that 1 plus V1 0, so its 0 mean part is greater than half. So this 1 plus the 0 mean part of V1 is bounded away from 0 almost everywhere on 0, 1. And if you can choose such an object, then you can define a time reparametrization in this sense. So you can see that this map sends 0 to 0, 1 to 1. Fine. It is monotonic. It is absolutely continuous. It is monotonic because of this condition. It is absolutely continuous. So it's a Lipschitz change of time. And then here you have the change of coordinates, right? So you take V1 and V2, and you substitute. So here you are. So I'm passing from 2 to 3 coordinates because here I'm splitting the L infinity control into its constant part and to the 0 mean part. So you take the average of V1. Here you have this complicated expression. Here you have this even more horrible expression. No, here you don't have -1. Sorry. So it's phi of V. But then, okay, whatever. This is a deformation. You can prove that this map is an homeomorphism, right? It has some families of fixed points. So constant controls are fixed. 0 mean controls are fixed. Controls of the form 0, V2 are fixed. And if you take a control V in the previous set, you see that your time reparametrization is well defined on this set. And you see that this set is full measured. So by the Sard lemma for absolutely continuous real functions. So this Sard lemma holds just in one dimension, which is what they need. I think it holds just in one dimension. Yeah. And well, so essentially your time reparametrization is well defined almost everywhere on 0, 1. So what is the magic of this reparametrization? That you compute f of rho of V1, V2. So you write here everything. The fact is that this part here, so this 1 plus V1, 0, is exactly phi dot, right? And here you have constants, so they do not depend on time. So essentially you see that here you have something which you can transform using a change of coordinates, right? And if you do the change of coordinates, this one, essentially everything reduces to this form, right? So the 0 mean part now really disappears. Essentially you have hidden all the 0 mean part of the control in the time reparametrization. So now what you see, now your variables are really the average of V1, so the constant part of V1, and V2. So you don't have any 0 mean part anymore. Just to show you what I imagine in my head, for example. So how it is done this set. So if the 0 mean part is of dimension 1, so suppose that you have a line, and then you have a family of cones, right, that are translated on this line. So really you have something like a roof, right? I don't know, I'm not really good at drawing. So you have a cone which is translated, right? But now you have to think that this is infinite dimensional, whatever. So, but now, I mean, this thing here described, let's say, a slice of the cone, right? So the time reparametrization hides all the dependence on the 0 mean part. Fine, so okay, you can prove that, as I told you, that my reparametrization map is continuous and it is an homeomorphism, right, with respect to the product topologies, essentially. Well, this one I already told you that the 0 mean part is hidden now. this point is important, and it explains why just in L infinity I can do this thing. Essentially because my time reparameterization preserves the direction of time. Essentially because 1 plus V1 0 is uniformly bounded away from 0. So what I'm really doing with the reparameterization of time is preserving its direction. So I cannot create loops. And if I cannot create loops, I cannot create brackets. So this is why my map cannot become open. Because if I don't have brackets, I cannot create new brackets keeping the direction of time. Because to create a bracket, I have to go back and forth in time. Right? So, okay, fine. Now what you do essentially, you reduced your map on the space R times L2 with this form. Now you know by the previous discussion that the Hessian is invariable. Fine, so what you do is you essentially solve all the coordinates which are spanned by the differential of G by the implicit function essentially. And then, okay, now you have to take care just of the first equation essentially, which you write as a quadratic form, so the Hessian map plus a remainder term of order at least 3. And then, okay, there is this generalized Morse lemma, which was proved by Agrachev in 1982, which tells you that you can do whatever you want now. So you can essentially solve the problem. And the spirit of this proof is much in the spirit of the Moser trick, right? So you construct a family of diffeomorphism which make this diagram commutative for every time on 0, 1. And your diffeomorphism is the flow of a non-autonomous vector field. So really, you write it down the condition of commutativity, you differentiate, you find the condition, and you see that everything works. Okay, so maybe I skip this part. Okay, now this is important. A problem. Now I'm able to solve everything, so I'm able to find a normal form on this space. So C1, C2, W2. The problem is that I want a normal form in coordinates V1, V2. So this one is the primitive. So I'm doing a Morse lemma now in a completion space, and nobody is telling me that the change of coordinates in the bigger space descends to a change of coordinates on the smaller space. But the fact is that here you can explicitly compute the change of coordinates. And you see that your change of coordinates is a Volterra integral equation, right? So it's an equation that reminds very much of the one defining the endpoint map. But this equation depends on C1, C2, and W2. The fact is that C1 and C2 are constants, so you can differentiate constants, no problem. Because now you have to see when the L2 part of this transformation is differentiable with respect to time. Because if it is differentiable with respect to time, then it means that I'm looking at an element in H1. And the fact is that this transformation is differentiable with respect to time if and only if W2 is in H1. So it is not an element in L2, but really an element in H1. So an element that belongs to the original space. And this means that my map preserves the smaller space, so preserves H1. And if it preserves H1, it preserves L2 by differentiation, right? But let me tell you once again that this is not clear, that if we had not reduced the first coordinate, we would have been able to differentiate this one, because W2 appears in the computation of the endpoint map. But here, if instead of C1 we had V1, so really the first control, we don't know how, in general, how to differentiate such a control. So in general, my transformation cannot be differentiable with respect to time. So it is not an element of H1. But here, everything works fine because we have done the preliminary change of coordinates. Okay, fine. And then some consequences. Let me just tell you the statements. What can I prove with my normal form is that every rank 2 nice singular curve is isolated among extremal curves in omega y in my strange topology. So in L infinity times L2, where by extremal curves I mean critical points of the extended endpoint map. So I'm looking at really at normal and abnormals, right? So geodesics. So my rank 2 nice curve is isolated among all these extremal curves. Okay, so here is basically the proof. Well, not important. Okay, and then I can also tell you this story. Is that rank 2 nice singular curves are isolated weakly in L2 among the singular curves in omega y. So here I'm really using the L2 times L2 topology, so the original one, which in principle is a weaker topology, very weaker topology. But essentially, the philosophy is that if you have a sequence of singular curves that converge to your nice singular curve, at some point they all become rank 2 nice, because the condition of being rank 2 nice is open. So all the controls here are smooth, so they are in L infinity, of course. And essentially you have a uniform convergence of the extremal trajectories associated to the curve. So you can recover by projection, and you see that your controls in fact are converging not just weakly in L2 but in L infinity. So the passage here is from weak in L2 to L2 and then to L infinity. So, and then your curve cannot be, and then UN cannot be singular by the previous proposition because it was isolated. So, open questions? Open questions, because I always like to finish with open questions. So, what is the local picture in L2? I don't know. Probably could be a mess. I don't know. So, what I really want to know, even for questions related to the heat diffusions or stuff like that, how deep is the singularity that nice singular curve provides? And essentially, rank 2 nice singular curve is optimal, right? So the singularity should be very, very, very deep. So how deep? I don't know. Maybe it's deep at infinite order. I don't know. I expect that this is very deep. So if somebody wants to try, please tell me something. And then can I infer? But I think that on this part, essentially, we are actually at a good point. That rank 2 nice singular curves are isolated among all extremal curves in L2. And I think the answer is yes. Now I'm pretty confident. I mean, we have something more than a sketch of a proof, so it should work. But in any case, if you can tell me something about the local picture of this set in L2, please. I'm here. And with that, I've finished. Thank you.
So, I believe we have questions. Can I have questions? What do you mean by deep?
Okay, no, but this is a deep. It means that let's take the point from another perspective. What does it mean that all the functionals are, I mean, no matter the functional you are trying to minimize is optimal, locally optimal. It means that the geometrical picture of your structure should be of a hole, of something like a black hole, right? So my question is, can you help me describing the hole in L2? Because now in L infinity times L2, I know what happens. It is a, I mean, you know that the singularity is quite ugly. In L2, I don't know. So essentially, I want to be able to characterize, to have a picture in mind.
In this meaning, it's
yeah, so the meaning is this one. How deep is the hole that you... Because the rank 2 nice curve is optimal. So it really has to be an obstacle for something. So which kind of obstacle, if you want? In L2, I don't know. But, I mean, the problem is, I admit that it seems quite hopeless, because already in L infinity times L2, I mean, you have an infinite dimensional space, so you have a cone over each point of an infinite dimensional space. It's a mess. I don't know. But so it's just philosophy if you want. But
Okay. Yes. So, flow of thoughts. But can you? Is it maybe that deep by deep you mean in how many directions you have a cusp?
no, it's in the sense that I mean all linear functional I cannot escape. So it's a minimal for all linear functional. Maybe it's a minimal for all quadratic functional. It's a minimal for functional of which order?
The upper point cannot be.
I mean, huh? Sorry.
How is that possible?
So this is in the spirit of what Montgomery wrote in his paper. So in his book. So you have something which captures all the, for example, all the lines. So I mean, my answer is vague because my image is vague. I don't know. But in some sense, it has to be a big obstacle, a big. So okay, do you know how they pictures black holes in physics, right? So they are deep singularities of the time space. Here, in some sense, the singularity is in terms, if you want, of how long are the brackets that you need to describe the singularity, if you want. And I suspect that you need a lot of brackets, because the singularity is really in the higher layers. If you can, because maybe it's at the infinite order, I don't know. So